Welcome to Civil Engineering Edge, where engineering concepts meet real-world innovation. In today's video, we explore how geothermal energy is transforming the way skyscrapers are heated and cooled. Hidden beneath the Earth's surface lies a powerful, constant energy source capable of reducing emissions, lowering costs, and reshaping modern building design. From dense urban cities to future smart skylines, geothermal systems are changing the rules of sustainable construction. Whether you're a civil engineering student, a practicing professional, or simply passionate about future-ready infrastructure, this video will give you clear insights into one of the most impactful energy solutions in modern civil engineering. Imagine a skyscraper heated and cooled without burning a single fossil fuel. What if the secret to perfect climate control for massive buildings was literally right beneath our feet? In this video, we uncover the hidden power of geothermal energy, an unseen giant beneath the Earth, the unseen giant, tapping Earth's core. When we admire a skyscraper, our attention naturally moves upward towards soaring heights, sleek glass facades, and impressive structural systems that define modern cities. Yet, the true powerhouse enabling these massive buildings to function efficiently is often hidden far below the ground. This is where geothermal energy emerges as an unseen giant in modern civil engineering. Geothermal energy refers to the natural heat stored within the Earth's crust. Unlike conventional energy sources, this heat is continuously available, unaffected by weather conditions, seasonal changes, or time of day. For skyscrapers where heating, ventilation, and air conditioning systems consume a major share of total energy, this stable underground heat source provides an extraordinary opportunity for sustainable climate control. By tapping into the Earth's consistent subsurface temperatures, engineers can regulate indoor environments with remarkable efficiency. During colder months, geothermal systems extract heat from the ground and transfer it into the building. In warmer months, the process reverses, moving excess heat from the building back into the Earth. This silent exchange happens without combustion, smoke, or harmful emissions. For civil engineers, geothermal systems represent a shift from traditional energy consumption to intelligent energy management. These systems integrate seamlessly with foundations, basements, and underground structural elements, making them ideal for high-rise construction in dense urban areas. This hidden thermal engine beneath our cities is quietly redefining how skyscrapers are heated and cooled, proving that the future of sustainable construction lies not only in the skyline above, but in the earth below. Imagine heating and cooling an entire city with no fossil fuels. Imagine a city where skyscrapers remain comfortably warm in winter and refreshingly cool in summer without burning coal, oil, or natural gas. This is the transformative promise of geothermal energy in the built environment. As urban populations rise and cities grow vertically, the demand for heating and cooling large buildings continues to increase dramatically. Traditional VIC systems rely heavily on fossil fuels, leading to high energy costs, carbon emissions, and long-term environmental damage. Geothermal energy offers a cleaner alternative by using the Earth itself as a heat source and heat sink. Instead of generating heat through combustion, geothermal systems simply transfer existing heat between the building and the ground. In winter, heat stored underground is brought up into the building. In summer, excess indoor heat is safely released back into the Earth. This process requires minimal electricity and produces almost zero direct emissions. Now imagine this system applied not just to a single building, but across an entire urban district. Multiple skyscrapers can share geothermal fields, creating centralized underground energy networks. Such systems reduce peak electricity demand, improve energy resilience, and significantly cut operational costs over time. For civil engineers and urban planners, this concept represents a fundamental shift from energy production to energy optimization. Cities powered by geothermal systems move closer to carbon neutrality while ensuring long-term thermal comfort for occupants. Heating and cooling entire cities without fossil fuels is no longer a dream, it is an engineering reality taking shape beneath our feet. Beyond hot springs, stable underground temperatures as a constant energy source. When most people hear the term geothermal energy, they imagine volcanic regions, hot springs, or geysers. However, skyscrapers in modern cities do not rely on extreme geological conditions. The true strength of geothermal systems lies in the stable and predictable temperature found just below the Earth's surface. At depths of only a few meters, the ground maintains a nearly constant temperature throughout the year, regardless of whether it is scorching summer or freezing winter above. This stability forms the foundation of geothermal heat pump technology. Instead of struggling against fluctuating outdoor air temperatures, buildings interact with a calm and balanced underground thermal environment. Geothermal heat pump systems circulate a fluid through underground pipes known as ground loops. These loops absorb heat from the ground during winter and release heat back into the ground during summer. Because the temperature difference is relatively small, the system operates with high efficiency and low energy consumption. For skyscrapers, where heating and cooling loads are continuous and massive, this constant energy source provides unmatched reliability. Equipment experiences less stress, system lifespan increases, and energy costs remain predictable over decades. From an engineering perspective, geothermal energy demonstrates that sustainable solutions do not always require advanced fuels or complex machinery. Instead, they rely on understanding natural processes and designing systems that work in harmony with them. Stable underground temperatures make geothermal energy one of the most dependable tools for future high-rise climate control. Setting the stage, skyscrapers above, silent power below. Look at a modern skyline and you'll see symbols of progress towering skyscrapers, reflective glass, and advanced structural systems pushing the limits of engineering. Yet, beneath this impressive vertical growth lies an entirely invisible network quietly supporting these massive structures. This is where geothermal energy operates out of sight, but critically important. Unlike conventional energy systems that dominate rooftops and mechanical floors, geothermal systems are hidden underground. Boreholes, ground loops, and heat exchange pipes are embedded deep beneath foundations, basements, and parking levels. Once installed, they operate silently with no smoke, noise, or visible mechanical activity. This hidden nature makes geothermal energy uniquely suited for dense urban environments. Skyscrapers can maintain clean architectural aesthetics while benefiting from a powerful renewable energy source below. For occupants, the experience is seamless, consistent indoor comfort without knowing the Earth itself is regulating the building's temperature. For civil engineers, this underground infrastructure must be carefully integrated during early design stages. Soil conditions, groundwater levels, foundation systems, and load-bearing elements all influence geothermal system performance. This creates an exciting multidisciplinary challenge where geotechnical, structural, and mechanical engineering intersect. As cities expand upward, space above ground becomes limited, but space below remains underutilized. Geothermal systems transform this underground zone into a functional energy asset. The result is a new paradigm in skyscraper design where the future of sustainable climate control is not found in the skyline, but silently embedded beneath it. How geothermal works simplified. Geothermal energy may sound complex, but its working principle is surprisingly simple. Instead of creating heat, geothermal systems move heat from one place to another. The Earth, just a few meters below the surface, maintains a stable temperature throughout the year. This natural stability becomes the foundation for efficient heating and cooling. In winter, geothermal systems collect heat from the ground and transfer it into the building. In summer, the process reverses excess heat from the building is pushed back into the cooler ground. This exchange happens through a network of underground pipes connected to a geothermal heat pump inside the building. Because the system works with steady underground temperatures rather than extreme outdoor air conditions, it consumes far less energy than conventional systems. There is no combustion, no fuel burning, and no direct emissions. For skyscrapers, this means reliable climate control, lower operating costs, and long-term sustainability, all powered by the silent thermal energy beneath the Earth's surface. The magic of heat pumps, moving heat, not making it. At the heart of every geothermal system is a powerful yet efficient device known as the geothermal heat pump. Its role is not to generate heat, but to transfer it, much like a refrigerator, just on a larger and smarter scale. This simple idea is what makes geothermal energy so efficient for heating and cooling skyscrapers. During winter, the heat pump extracts thermal energy from the ground through fluid-filled underground pipes. Even when the air above is cold, the earth below still holds usable heat. The heat pump concentrates this energy and transfers it into the building's interior, providing comfortable warmth across multiple floors. In summer, the process reverses. Excess heat from inside the building is absorbed by the heat pump and transported back into the ground, where it is naturally dissipated. This cooling process requires significantly less energy than traditional air conditioning systems because it works against a cooler underground environment rather than hot outdoor air. The key advantage lies in efficiency. By moving heat instead of creating it through combustion or electrical resistance, geothermal heat pumps can deliver 3 to 4 units of heating or cooling for every unit of electricity consumed. For civil engineers, understanding this mechanism is crucial. The heat pump connects structural design, mechanical systems, and energy efficiency into one integrated solution, making geothermal technology a cornerstone of sustainable high-rise construction. The silent underground network, loops and pipes beneath the foundation. Beneath every geothermal-powered skyscraper lies a hidden network that most occupants never see, an underground system of pipes and loops that quietly exchange heat with the earth. This silent infrastructure is the backbone of geothermal heating and cooling. These underground pipes, known as ground loops, are typically made from high-density polyethylene and are buried either vertically or horizontally depending on site conditions. In dense urban areas with limited land, vertical boreholes are drilled deep beneath the building foundation, sometimes extending hundreds of meters into the ground. A fluid circulates through these loops, absorbing heat from the earth in winter and releasing heat back into the ground during summer. The process is continuous, silent, and highly efficient. Once installed, the system requires minimal maintenance and can operate for decades. From a civil engineering perspective, this underground network must be carefully coordinated with foundation design, soil properties, groundwater levels, and structural loads. Proper planning ensures thermal efficiency without compromising structural safety. What makes this system remarkable is its invisibility. There are no chimneys, cooling towers, or noisy outdoor units. The energy exchange happens silently below ground, allowing skyscrapers to maintain clean aesthetics while benefiting from renewable energy. This hidden thermal network transforms the ground beneath buildings into an active energy partner, quietly supporting climate control every single day. Dispelling myths. It's not about volcanoes. One of the most common misconceptions about geothermal energy is that it requires volcanoes, geysers, or extremely hot underground conditions. In reality, geothermal systems used in buildings rely on something much simpler: the consistent temperature just a few meters below the Earth's surface. You don't need to live near volcanic zones to use geothermal energy. Almost every location on Earth has stable subsurface temperatures suitable for geothermal heating and cooling. This makes the technology widely applicable, even in urban centers far from natural geothermal hotspots. The system does not tap molten rock or deep magma. Instead, it interacts with shallow ground layers where temperatures remain nearly constant year-round. This stability is what allows geothermal systems to operate efficiently in both hot and cold climates. For civil engineering students and professionals, understanding this distinction is important. Geothermal building systems are not power plants, they are thermal exchange systems. Their purpose is not to produce electricity, but to efficiently regulate indoor temperatures. By clearing up these myths, geothermal energy becomes less intimidating and more practical. It is not an exotic or risky technology, but a proven engineering solution already in use worldwide. Once this misconception is removed, geothermal energy stands out as one of the most reliable, scalable, and environmentally responsible options for heating and cooling modern skyscrapers. Skyscrapers as geothermal titans. Skyscrapers are often seen as symbols of high energy consumption, but with geothermal systems, they can become leaders in sustainable design. These massive structures, once dependent on fossil fuel-based heating and cooling, are now transforming into geothermal titans buildings that use the Earth itself to regulate their climate. By tapping into underground thermal stability, skyscrapers can significantly reduce their energy demand while maintaining comfort for thousands of occupants. What makes this shift powerful is scalability. The larger the building, the greater the potential benefits. Reduced operating costs, lower emissions, and long-term resilience make geothermal systems especially attractive for high-rise structures. Across the world, engineers are proving that geothermal technology is not limited to small buildings or new developments. Even dense urban skylines are being retrofitted with underground energy systems. These towering structures are no longer just architectural landmarks, they are becoming active participants in the global transition toward cleaner, smarter cities. Case study: New York City's booming geothermal retrofits. New York City is one of the densest urban environments in the world, filled with aging high-rise buildings, underground utilities, and limited open space. For many years, this made geothermal energy seem impractical. Yet today, NYC is emerging as a powerful example of how geothermal retrofits can succeed, even in crowded urban jungles. With rising energy costs and aggressive climate goals, building owners are turning to geothermal systems to replace outdated fossil fuel-based heating and cooling. Engineers use vertical boreholes drilled beneath existing buildings, sidewalks, and courtyards to access stable underground temperatures without disrupting city life above. One of the biggest breakthroughs has been combining geothermal retrofits with major building renovations. Old steam boilers and chillers are replaced with geothermal heat pumps, dramatically improving energy efficiency. In many cases, buildings reduce heating and cooling energy use by over 40%. These projects prove that geothermal energy is not just for new skyscrapers, it is also a powerful tool for decarbonizing existing structures. Careful planning, advanced drilling techniques, and detailed geotechnical studies make it possible to integrate geothermal systems even in space-constrained sites. For civil engineers, NYC's experience demonstrates that urban complexity is not a barrier, but a challenge that can be solved through smart design and multidisciplinary coordination. Beyond efficiency, long-term cost savings, and carbon reduction. While energy efficiency is often the headline benefit of geothermal systems, the long-term economic and environmental advantages are even more compelling, especially for skyscrapers. These massive buildings operate continuously, making their lifetime energy costs extremely high. Geothermal systems significantly reduce operational expenses by cutting heating and cooling energy consumption. Although initial installation costs may be higher, the savings accumulate year after year. Over the lifespan of a skyscraper, this can translate into millions in reduced utility bills. Maintenance costs are also lower. With fewer moving parts and no combustion-based equipment, geothermal systems experience less wear and tear. Underground components can last 50 years or more, while heat pumps often exceed 25 years of operation. From an environmental standpoint, the impact is substantial. By eliminating on-site fossil fuel combustion, skyscrapers drastically reduce carbon dioxide emissions and improve local air quality. This helps cities meet climate targets while creating healthier indoor and outdoor environments. For developers and engineers, geothermal systems offer both financial stability and regulatory advantages. Buildings with lower carbon footprints are increasingly favored by green building certifications and government incentives. In the long run, geothermal energy transforms skyscrapers into sustainable investment structures that are not only efficient today, but resilient and environmentally responsible for decades to come. Engineering marvels. Integrating geothermal into towering designs. Integrating geothermal systems into skyscrapers is an engineering challenge that requires close collaboration between architects, civil engineers, and mechanical engineers. These towering structures demand careful planning to ensure that underground energy systems complement rather than interfere with structural performance. Geothermal systems are typically integrated during the early design stages. Boreholes and ground loops are coordinated with foundation layouts, basements, and pile systems. In some cases, foundation piles themselves are used as energy piles, serving both structural and thermal functions. Architects benefit from geothermal integration because it reduces the need for large rooftop mechanical equipment. This frees up valuable space for amenities, green roofs, or additional floors. From a design perspective, buildings become cleaner, quieter, and more efficient. Civil engineers must consider soil conditions, thermal conductivity, groundwater movement, and load distribution. Detailed modeling ensures that heat exchange does not affect soil stability or foundation performance. These systems represent engineering at its best where sustainability, structural integrity, and architectural ambition come together. Skyscrapers powered by geothermal energy are not just tall buildings. They are carefully engineered ecosystems that blend technology with nature, setting new benchmarks for future high-rise design. The global shift. Why now, across the world, cities are rethinking how buildings consume energy. Climate change, rising energy costs, and increasing urban density have made traditional heating and cooling systems unsustainable. This is why geothermal energy is gaining global attention, especially for large structures like skyscrapers. Unlike fossil fuel-based systems, geothermal energy offers a reliable, low-emission solution that works continuously. Advances in drilling technology, heat pump efficiency, and system integration have made geothermal systems more practical and cost-effective than ever before. At the same time, governments, developers, and engineers are under pressure to meet aggressive sustainability targets. By 2030, many cities aim to drastically cut carbon emissions from buildings. Geothermal energy directly addresses this challenge by reducing operational emissions while improving energy efficiency. The global shift toward geothermal is not driven by a single factor, but by a convergence of policy, economics, and engineering innovation, making now the critical moment for its widespread adoption. Policy and incentives. Governments driving sustainable construction. Governments around the world are playing a crucial role in accelerating the adoption of geothermal energy in buildings. As climate commitments grow stronger, policymakers are recognizing that buildings account for a significant share of global carbon emissions, especially in urban areas dominated by high-rise structures. To address this, many countries have introduced strict energy efficiency standards, carbon reduction targets, and green building codes aimed at 2030 and beyond. Geothermal systems align perfectly with these goals by offering a low-emission solution for heating and cooling. Financial incentives are another major driver. Governments provide tax credits, grants, low-interest loans, and subsidies to offset the higher upfront costs of geothermal installations. In some regions, building owners receive additional benefits such as reduced property taxes or priority approvals for sustainable designs. For civil engineers and developers, these policies reduce financial risk and encourage long-term investment in geothermal systems. Regulations are no longer just restrictions, they are becoming enablers of innovation. Urban authorities are also encouraging geothermal retrofits in existing buildings, not just new construction. This ensures that sustainability efforts extend across entire cityscapes rather than isolated projects. As 2030 sustainability deadlines approach, geothermal energy is increasingly viewed not as an optional feature, but as a strategic necessity supported and accelerated by global policy frameworks. Energy independence, stability in an uncertain energy world. One of the most compelling reasons for the global shift toward geothermal energy is energy independence. Traditional heating and cooling systems depend heavily on electricity and fossil fuels, both of which are vulnerable to price volatility, supply disruptions, and geopolitical uncertainty. Geothermal energy, in contrast, is local and stable. The heat stored beneath the ground does not need to be imported, transported, or refined. It is available on-site continuously and predictably. This makes it an ideal solution for large buildings seeking long-term energy security. For skyscrapers, which consume enormous amounts of energy daily, reliance on volatile energy markets can create financial risk. Geothermal systems reduce this exposure by significantly lowering external energy demand. From a city-wide perspective, widespread adoption of geothermal systems helps stabilize power grids by reducing peak loads during extreme weather conditions. This improves resilience and reduces the risk of blackouts. For civil engineers and planners, energy independence is not just an economic advantage, it is a design consideration. Buildings powered by geothermal systems are less vulnerable to future energy crises and regulatory changes. By tapping into the Earth's natural heat, cities can regain control over their energy future, creating built environments that are not only efficient, but resilient and self-reliant. Future-proofing cities, geothermal in smart urban planning. Future cities must be more than tall and dense. They must be smart, adaptable, and resilient. Geothermal energy fits seamlessly into this vision by providing a reliable foundation for sustainable urban development. As cities adopt smart infrastructure, energy systems are becoming increasingly integrated with digital monitoring, automation, and predictive control. Geothermal systems pair well with these technologies, allowing real-time optimization of heating and cooling based on occupancy and weather conditions. From an urban planning perspective, geothermal energy supports long-term resilience. Underground systems are protected from storms, heat waves, and external disruptions, making them more reliable than exposed energy infrastructure. Geothermal also enables district-level energy planning, where multiple buildings share underground thermal resources. This improves efficiency and supports coordinated urban growth. For civil engineers, geothermal systems encourage holistic design thinking where structural, mechanical, environmental, and energy systems are planned together from the earliest stages. By incorporating geothermal energy into city planning today, engineers help create urban environments that remain functional, efficient, and sustainable for decades. In this way, geothermal energy becomes not just a building technology, but a cornerstone of future-ready cities. Your role in the geothermal revolution. Geothermal energy is not just a technology for massive skyscrapers or iconic city skylines. It is a solution that involves everyone. From civil engineering students designing future buildings to professionals shaping today's infrastructure, geothermal systems offer an opportunity to actively participate in the global shift towards sustainability. As cities expand and energy demands increase, the decisions made by engineers, architects, developers, and homeowners will define how environmentally responsible our built environment becomes. Understanding geothermal technology empowers you to make smarter choices whether you are planning a high-rise, renovating an existing building, or selecting systems for your own home. This is not about distant policy goals or abstract sustainability targets. It is about practical action, informed design, and long-term thinking. The geothermal revolution is already underway, and your awareness, decisions, and advocacy can directly influence how fast and how effectively it reshapes the future of energy-efficient buildings. Beyond skyscrapers, scaling geothermal to homes and small businesses. While geothermal systems are transforming skyscrapers, their true strength lies in scalability. The same technology used to heat and cool high-rise buildings can be adapted for individual homes, apartment complexes, schools, and small businesses. This makes geothermal energy one of the most flexible renewable solutions available today. For residential buildings, geothermal heat pumps provide consistent indoor comfort with significantly lower energy consumption. Homeowners benefit from reduced utility bills, quieter operation, and long-lasting systems. Small commercial buildings, such as offices and retail spaces, gain similar advantages with improved operational efficiency and lower maintenance requirements. The installation approach may vary based on available space and soil conditions. Horizontal loops are often used for homes with open land, while vertical boreholes are suitable for urban plots with limited space. Regardless of scale, the core principle remains the same, using stable underground temperatures for efficient heat exchange. For civil engineers and students, this scalability is crucial. It means geothermal energy is not limited to mega projects, but can be applied across diverse building types. This broad applicability increases demand for skilled professionals who understand geothermal design and implementation. By recognizing that geothermal systems work at every scale, we move closer to widespread adoption, transforming entire communities, not just skylines, into energy-efficient environments. The investment angle. Is geothermal a smart long-term choice? When evaluating geothermal energy, one of the most common questions is whether it makes financial sense. While the upfront installation cost is typically higher than conventional systems, geothermal energy should be viewed as a long-term investment rather than a short-term expense. Geothermal systems dramatically reduce monthly energy bills by cutting heating and cooling costs. Over time, these savings accumulate, often allowing the system to pay for itself within a reasonable period. Additionally, geothermal equipment has a longer lifespan, reducing replacement and maintenance expenses. From a property perspective, buildings equipped with geothermal systems often see increased value. Energy-efficient structures are more attractive to buyers, tenants, and investors, especially as sustainability becomes a priority. For professionals and students planning future projects, geothermal energy represents risk mitigation. As energy prices rise and regulations tighten, buildings with geothermal systems remain protected from sudden cost increases. The financial benefits are not just individual, they extend to communities and cities by reducing strain on power grids and lowering long-term infrastructure costs. Viewed through a long-term lens, geothermal energy is not just environmentally responsible, it is economically intelligent, offering stable returns, operational savings, and future-ready resilience. Call to action. Taking the first step toward a greener future. The transition to geothermal energy begins with awareness and action. Whether you are a student, engineer, building owner, or homeowner, the first step is to explore the opportunities available in your region. Many governments and local authorities offer incentives for geothermal installations, including tax credits, subsidies, and low-interest financing. Understanding these programs can significantly reduce initial costs and make geothermal systems more accessible. Education is equally important. Learning about site feasibility, soil conditions, and system design helps ensure successful implementation. Civil engineers and students can play a vital role by advocating for geothermal solutions during planning and design stages. Beyond individual projects, pushing for greener energy choices helps shape broader change. Supporting sustainable building practices influences developers, policymakers, and communities to invest in cleaner technologies. Geothermal energy represents a future where buildings work in harmony with the earth rather than against it. By taking informed action today, whether through design decisions, professional advocacy, or personal investment, to become part of a movement that is reshaping how the world heats and cools its buildings. The revolution is already beneath your feet. The next step is yours. Geothermal energy is more than a renewable technology. It is a smart engineering solution shaping the future of sustainable buildings. From towering skyscrapers to everyday homes, the power beneath our feet is redefining how we design, build, and operate structures. As civil engineers and future professionals, understanding these systems allows us to create energy-efficient, resilient cities. If you found this video valuable, support Civil Engineering Edge by liking, sharing, and subscribing for more in-depth engineering insights. Let us know your thoughts in the comments and stay connected as we continue exploring the technologies driving the future of civil engineering. Below are clear, high-impact key points written segment-wise, exactly how you'd use them for video slides, on-screen text, narration cues, or revision notes on Civil Engineering Edge. I've kept them engineering-focused, easy to follow,